Hello student, welcome to our physics discussion, that is physics in a start way. Physics in a smart way. Okay, I'm sorry. We go for the next process, that is constant temperature process, which is popularly known as isothermal process. Constant temperature process, we know the name is self-sufficient, self-understanding, the meaning comes out. The temperature is constant. Out of the three variables, one is pressure, second is volume, third is temperature. Once you say temperature is constant, if you look at the right hand side, on the right hand side, you know number of moles. Once you select the gas, the number of moles you cannot change. R is universal gas constant. It is not within our powers to change it. That is 8131 as you know it in SI. And now we say temperature is constant, so right hand side becomes constant. The moment right hand side becomes constant, we know PV equal to constant. If you consider pressure along y-axis and volume along x-axis, and pressure along x, volume along y, so that says that y into x equal to constant. Y into x equal to constant means x is proportional to y, or y is proportional to 1 by x. Sorry, x is proportional to 1 by y, or y is proportional, or x is proportional to 1 by y, or y is proportional to 1 by x. All those things will be required when you consider the graphs and all that. Okay. So for a state equation is there. State equation, we now know PV equal to constant. What is that constant? We know that constant is nothing but nRT. That is the state equation. Number two, we got work done. Work done, W. We know work in this case, we should not rely on the formula P delta V, because that is not a constant force work. Here, there is structure or there is restriction only on temperature. In the entire process, pressure and volume, they are supposed to change. We shall be talking about all those changes, reversibility, irreversibility, all those things during the last part of this process, or during the subsequent video, which will be spillover of this process. So thereby, we got here the work done. We got the work done. And here work done, we cannot write that is equal to P delta V. P delta V will be wrong. So thereby, we know there is an alternative formula for work. That is the work only when variable force is there. When the force is variable, that is integration PdV. That is integration PdV. If the gas expands from a volume V0 to volume V1, so that is the work done. If you go for the process, then let me remove some portion of this thing. We know that PdV equal to PV equal to nRT. So if a student likes, he or she can write down P equal to, that is nRT IV, or V equal to nRT by P. Here in the integration process, we are involved with a situation where pressure is variable and volume is variable, but these two are different variables. Different variables. It is just like integration y dx, but don't confuse. If y and x are independent variables, then that's a very serious case. You cannot most possibly solve it. But unfortunately, there is a link which is temperature, which connects these two things here. So thereby, as you go for the integration, this has to be done. That is integration starting from initial volume V1, if the gas expands to final volume, starting from initial volume V0 to final volume V1, PdV, P can be expressed as nRT by V. nRT by V dV. Here we know that N is constant, R is constant, T is constant, integration V0 to V1. We got dV by V, d by V. So here we got a situation that is integration of dx by x or dy by y. Thereby the answer is ln x. That is a typical logarithm. That is rational logarithm. We shall be coming to know. Okay, the teacher must have very learned here in this case. That is nRT ln v v2 v1 v0 v1. That will be, let me remove that will be nRT ln v1 minus ln v0. Some formulas do exist. One is that if we are having ln A minus ln B, then that can be expressed as ln A by B. You'll be automatically knowing that going to logarithms. That is nRT into ln V1 by V0. That is the value of the water. So here, once you have covered, that is nRT ln V1 by V0. And it can be also, this thing can also be changed into a form that we know PV equal to constant. PV equal to constant. Because PV equal to constant, we must let me clear up a state. Let me clear up some states. So back term W equal to these things they have further utilization over. We may be getting it up. Number two, that is back term W equal to the last step that we got, that is T on V2 by V1. But we know because PV equal to constant, sometimes the uh, this equation may be quite useless for you. The data that is given may be in a slightly different format. So PV equal to constant, I may write down as because PV equal to constant, so P0 V0 P0 P0 must be equal to P1 V1, which is final pressure and volume. So in the bracket we got V1 by V0. So V1 by V0, we clearly see that comes out as P0 by P1. So if the data, if your question is in pressure format, so that will be exactly ln ln P0 by P1. Or also can be kept in this way. Okay. So the things is also number three. We go for the next one, that is first law. First law of thermodynamics. which says Q equal to delta U plus W. As you know already that delta U, that is the change of internal energy. We know delta U is that is known as state function. It doesn't depend upon the path of those things. I'll be talking on all those things, those are the details. So thereby, delta U depends upon temperature change, that is delta T. Because the delta U has got a formula that is NCV into del T. NCV into del T. And when del T is zero, there is no temperature change. Temperature is not allowed permitted. So delta U equal to zero. The moment delta U equal to zero, Q becomes W. Now you can see when you compare this with constant volume process, isoperic process, here the gas behaves like a perfect monk, extremely spiritual, extremely religious. The gas says, I don't want to keep anything that you give me. Whatever heat, whatever thermal energy you give me, I'll be just transferring to outside, maybe to spring or something like that. I won't be keeping anything, any part of that. So gas behaves in the most selfless way. The gas behaves in the most selfless way, just like a monk. So that is the first law of the set of the first law. Okay. So once you got that, let us go for the other things. Number four. Number four, first law, sorry, number four, that was the specific heat. Specific heat. Specific heat for any substance, that is Q by E, especially for a gas, Q by N delta T, molar specific heat. But because your delta T tends to zero, so thereby specific heat tends to be infinite. So due to that, we could say isothermal specific heat of a substance tends to be infinite or is infinitely large. That gives an impression as if the body is a great hole. You are adding heat, but temperature doesn't change. So that shows the body as if it is so massive. You are adding heat, but heat is simply getting lost within the object, within the body. That seems to be getting lost. So that is the idea, the specific here. Number five, number five, let me remove all those things. Number five, clear up the space of the graphs. Temperature is constant if I take temperature on x-axis and pressure on y-axis PT graph. That's the temperature graph. So temperature is constant, so thereby the graph will be like this. Sorry, sorry, sorry. Just a minute. don't make the graph touch the x-axis or temperature axis. If you touch it, then that shows pressure equal to zero. That happens at absolute zero. That is not possible. That is not possible as per a particular law, third law of thermodynamics. Okay. Second, graph temperature on x-axis, volume on y-axis. Thereby, we know the graph also will be like this. Okay. The third one, so pressure temperature graph is called, volume temperature graph is called. Third graph is pressure volume graph, where both pressure is on y-axis and volume is on x-axis. Both are variables. Already you have seen that the equation we got y is proportional to 1 by x, or x into y equal to constant, or x is proportional to 1 by y, or xy equal to constant. These type of graphs, they we usually brand it by or that is hyperbola. That is like this. You know, y is proportional to 1 by x. But when x increases, y decreases. Whenever y increases, x decreases. You know, so thereby the graph is like this. So that is the graph is a rectangular hyperbola. Is a rectangular hyperbola. You must remember it. Keep that in mind. The graph is like this. When the graph goes towards the volume axis, x-axis pressure decreases, or coming back pressure increases. The graph is like this. A rectangular hyperbola. Okay. There is some extra additional information regarding this graph, practicality and all that. I will be discussing that in the next process, that is adiabatic process. But now our 5 points are over. Once the 5 points are over, there is another issue that we can say, that is number 6. Number 6, that is practicality. That is practicality of the process. But I think my video is sufficient to learn. In the next video, I'll be discussing that. That will be an interesting discussion. How to execute an isothermal process, or what are the problems those are encountered when making this isothermal process, and how theoretical isothermal process and practical process is linked with reversible and irreversible processes. We will be getting to those issues, those theoretical issues, that is practicality. So thank you. Today, next class, we shall be going through all those things.